So good morning, everyone. I'm Aden, and thank you for coming to my talk this early in the morning. So today we're going to talk about defensive security. Today we're going to talk about .NET, or more specifically, how .NET attacks are not so hidden from us. So before I begin, just a quick introduction about myself. So just 4 things. I'm a threat hunter at Countercept and from MWR Info Security. So we are a consultancy firm, and I belong to the detection and response team. And my job is literally detection and response. For the detection part, I do something known as an hypothesis-driven hunting, where I sift through all my client data. I hunt for anonymous events, and event where I find something suspicious, I investigate it. So hence the response part, where I use various telemetries like process loggings, event logs, MFT to aid me in my investigation. So I'm also somewhat of an attack detection blogger. So as part of my job being a threat hunter, I need to do quite a bit of attack detection research because, as we all know, the bad guys are always constantly upskilling themselves. So we as the defenders, we as the good guys, we have to upskill ourselves as well. So in events where I find something interesting or big enough, I'll blog about them and put it on the Countercept web portal. So we have actually quite a bit of cool research going on the Countercept web portal, so feel free to just jump in. And I'm also a bit of a code junkie. I like to write scripts, write code to automate activities. And I literally wrote a script once to help me decide what to eat for lunch on the current day, because I have no idea what to eat for lunch. So yeah, some of my first world problems. And lastly, I'm a Netflix addict. When I'm just I have nothing to do, literally just bored out of mind, I'll just literally chill and just watch Netflix. So anyway, let's move back to the agenda, which is why we are here today, other than the free beer that's going on at the after party. So we only have 2 agendas today. Firstly, the importance of .NET detection. Why do we need to do it? And basically, why do we do .NET detection? Also, I'm going to talk about how we actually do the detection portion itself. So I'm going to first start on why the need to do .NET detection. So a little bit of history. As a threat hunter in Countercept, I have seen my fair share of adversary, and I've faced my fair share of investigation. And among the threat actors that I face, most of them use script-based attacks. And probably because these script-based attacks are linked to binaries or processors that are installed by default on a Windows machine. So I've seen PowerShell invoking download string, trying to run a Mimikatz program. I've seen VBScript trying to enumerate user drives. I haven't seen those pesky little macros that try to trick users into clicking them to get a free iPhone. So out of all these script-based attacks, PowerShell is a hot favorite. Probably because, it's a really, really powerful tool. It's a really powerful administrative tool. With it, a threat actor can actually abuse it to load shellcode into memory, call upon the .NET API, which is essentially what PowerShell is based on, and going as far as calling upon the native API as well. And if you think about PowerShell in general, it's quite easy to POC it. All you need to do is to fire up a console, test your code, and I'm pretty sure if you just do a quick Google search on PowerShell framework, you could easily get 20 hits easily. But as defenders, we are also getting better. As compared to in the past, PowerShell attacks are not as hard to detect as it was before. With the rise of EDR agents, it brings about a different set of telemetries in which defenders can actually leverage on, such as analyzing parent-child process relationship. Like my example here. From here, we see Word document or Excel spreadsheet spawning PowerShell, which is very anomalous. You will not expect a Word document to actually need to spawn PowerShell. And to be honest, I've actually seen legitimate usage of this throughout my client data. There are actually some legitimate usage, but it's very rare. And probably when you see such a behavior, most of the time, it's probably anonymous and perhaps malicious. We can also look at the command line arguments that comes with a newly spawned PowerShell process. Like in this case, we see that the PowerShell is simply just outputting a command. This is an evil command. So we know nothing bad. But what if the PowerShell was actually running Mimikatz or something else? So with this level of visibility, defenders can actually better see what is actually happening, what a PowerShell process is attempting to do. There are also other defenses, such as MZ, that can assist antivirus with script-based attack detection. So MZ is essentially an interface that sits between a PowerShell process and the antivirus. When the command is entered to the PowerShell console, it will be sent to the MZ interface, which will in turn send to the antivirus. And if a signature is created, the command will be blocked. So like my example right here, I actually entered MZ into the command prompt, but before it was executed, it was sent to the antivirus via MZ. And because the signature has been created, the execution actually stopped. So another defense that we have is PowerShell script block logging, which actually can aid with defenders as well. So any commands entered within a PowerShell console, it will actually be logged within the event ID of 4104 for later versions of PowerShell. So to just give a summary of what we have actually discussed, as an industry as a whole, we have gotten better. We are given more opportunities to detect malicious PowerShell. And I think we deserve a pat on our back. But, as always, there's a but. Bad guys, they just don't give up. Being bad guys are aware of the challenges that PowerShell face, so they're moving on to different techniques and attack to evade current defenses. And one of the attacks they've chosen is actually .NET attacks, whereby you invoke the .NET core directly, .NET framework directly, instead of through, for example, PowerShell. So I'll touch on to what I mean by this statement in a couple of slides later. But first, let's ask ourselves a question. Why .NET? Well, if you think about it, .NET is rather similar to PowerShell, right? It's powerful. It's installed by default on most Windows machines. But with one key difference, there's currently a lack of telemetry towards .NET attacks. And I'll show it with an example here. So I'm going to do a demonstration, a video demonstration, with comparing PowerShell and .NET. So both of them are going to do exactly the same thing. Firstly, they're going to write a registry key through the use of the .NET API. Secondly, they're going to pop a message box through the use of a Windows native API. So native API is essentially how the Windows OS communicates. Basically, the Windows native API. So I have a demo here. So right here, as you can see, I have a PowerShell HCA file and a .NET HCA file. So I'm going to click on my PowerShell HCA file first. So just wait for the video to load. So I'm going to click on my PowerShell HCA file, and I'm going to execute PowerShell code. So as you see, I pop a message box. I wrote a registry key. And now we're going to see what are the indicators left by this particular example. So I'm going to use event log sysmon to look at the process logging. And as you can see here, we see a PowerShell process being spawned, and it was spawned by an MSHA process, which is rather anomalous. You won't expect MSHA to spawn PowerShell typically. And if you look at the command line arguments, we actually see a PowerShell base64 encoded command. So with this visibility, as a defender, I can attempt to decode this command. So I can use a tool like CyberChef, paste in my encoded commands, base64 decode it, and once I decode it, I can actually see what the PowerShell code was being run, giving me visibility on how to react. And as a defender, with this visibility, I can know how to react and how to advise my clients on what to do. So I'm just going to clear out all my artifacts now, and I'm going to run the .NET payload now, and I'll show you the visibility that we can see from it. So I'm just going to close the PowerShell HCA file and open the .NET HCA file. And now I'm going to execute it. Same thing, I pop a message box. Same thing, I created a registry key. And now, let's look at the event logs again. Let's look at the process logs through sysmon. And as you can see, that's all we have. We see an MSHA process running a HCA file. And with this level of visibility, as a defender, I'm actually limited in what I can do. All I can see is just a HCA file being executed. And to further investigate, I will actually need the HCA file to acquire the HCA file to look at it. So to just give a summary of what I actually demonstrated in this video, for the PowerShell payload, with MSHA process, I spawned a PowerShell process which was used to write a registry key and pop a message box. With the .NET HCA, however, I use MSHA process to call the .NET framework directly. So there's a question here. How did I actually achieve this? And this is something known as an in-memory assembly loading technique. So I actually have a flowchart which I will show you now how this was actually performed. So first, on my attacker's machine, I have a C# code. I will compile the C# code into a .NET assembly. Next, I will serialize it. So you can actually do it with James Forshaw .NET JScript technique or other particular tools that you want. After serializing it, I will embed it into a delivery mechanism. So in my case, I use a HA file as my delivery mechanism, but typically you can use any other delivery mechanism of your choosing. Once I deliver it to my victim's payload, I will load it into memory. And when it's loaded into memory, deserialize it back to the .NET assembly. And once it's deserialized, I will instantiate an object out of it. So basically, this entire flowchart, if you are aware of object-oriented programming, you realize that this entire flowchart is very similar to these 3 lines of code, whereby these are 3 lines of C# code, whereby I attempt to reference an assembly. With that assembly, I'm able to call upon a class constructor, and once I call upon its constructor, I can invoke its methods. So essentially, these 3 snippets of code were the entire flowchart that I was trying to do was actually attempting to replicate these 3 lines of codes. And now that I have this loaded object, what can it do? Basically, anything PowerShell can do, it can do, since they're all basically backed by the .NET framework. So to just give a midpoint check on what we have discussed so far, we have a loaded object right now, which we created through the use of an in-memory assembly. This loaded object can do whatever PowerShell can do, but with one key difference. There is a current lack of telemetry towards it. So this is what we're going to discuss, and this is our challenge today. Can we detect this? And now I'm going to move on to the second agenda of my topic. How do we actually do the detection portion itself? So I'm going to do some informal initial triage first with Process Hacker. So for those of you who are unaware of what Process Hacker is essentially a tool that allows you to analyze a process properties such as its threads performance, the module loads, and I'm going to use it to analyze the MSHA process that was used to run the .NET HA file. And with it, firstly, we'll look at the module loads within the MSHA process. And we can see something interesting. We can actually see that within the module loads, there are a couple of .NET runtime DLLs that were being loaded. And this makes sense because initially, the MSH process was running a .NET assembly, hence it requires this runtime engine. So this is so very suspicious, right? If we think back on the behavior of MSHA, what does it do? It typically only runs HTML or JavaScript code. So it's pretty dodgy. And this logic doesn't only apply to MSHA process. You can actually apply it to other binaries that typically do not execute .NET code. And with this, we can think of a hunt hypothesis, whereby we can actually have a hypothesis to hunt for the presence of .NET runtime DLL in these binaries. So this can actually help us to flag out certain anomalous activity. But as usual, there's always a but. What if the threat actor were to use a binary related to .NET, such as msbuild.exe, whereby msbuild.exe is a .NET application that allows you to build .NET application? Or rather, a third-party software like SQL Server, whereby you can actually use SQL Server to execute C# code. So with these processes, it's not uncommon for them to actually have a .NET runtime DLL. So we need something better. And fortunately for us, the answer to this actually lies deep within Process Hacker. So in Process Hacker, there's a column that typically don't appear by default. It only appears when it detects events related to the loading of .NET assemblies. And I'd like you to focus on one of the assembly in particular, basically my assembly. So if you look at it, you realize, and you compare to the other assembly load, you realize there is a lack of path, which is a very strong indicator of a potential in-memory assembly load. The other assembly has a path because they are located on a disk, hence the path. But in this case, because there wasn't any found on this, there's no path. So we'll touch more onto in-memory assembly loads in later slides, but let's ask ourselves another question here. How did Process Hacker achieve this? So it turns out that in Process Hacker, deep within it, it actually utilized a set of .NET ETW providers. So ETWs are basically event tracing for Windows. Essentially, wherever something happens in Windows, and it will be logged. So essentially, any .NET events will be logged within Windows. So with this here, it's essentially a wealth of information that we can actually leverage on. And we at Concept, we created a Python POC script by leveraging on FireEye's ETW tracing library to consume these .NET ETW events. And now, with this new level of visibility, let's try to detect the payload that I run in the prior demonstration. Let's try to find indicators related to in-memory assembly load. Let's try to find indicators related to the registry creation through the use of .NET API. And finally, let's try to find indicators related to the invoking of native API. So let's go back to our discussion on in-memory load. Let's look again on events related to in-memory assembly loading indicators. So as I mentioned earlier, with the use of Process Hacker, we actually are able to find out events related to the loading of .NET assembly, and with it, we have strong indicators related to in-memory assembly loading. There's another event that we can use though, and it's something known as just-in-time compilation. So before I dive deep into what just-in-time compilation events are, we need to understand how the .NET code compilation architecture look like. So .NET is a managed code. Essentially, it runs within a managed environment. It don't compile to native code directly. So when a .NET code compiles, it compiles to something known as the CIL, the Common Intermediate Language. This CIL, upon execution, it will be run through something known as the JIT compiler, the just-in-time compiler. And with it, it will be compiled to a native code. Once it's been compiled to a native code, it will be cached, and the JIT compiler will not be used again. All right, for this particular process. So this is interesting because wherever the JIT compiler is used, an event will be generated. So essentially, an event will be generated whenever a .NET method is first utilized, because it will be put through the JIT compiler. After it's been put through the JIT compiler, it will be cached, so no instances of the event will appear. So to just give a summary of what we can use to detect in-memory assembly loading, we can use events related to the loading of .NET assembly, and we can use events related to just-in-time compilation. So I have an output from Concept's Python POC code here. Firstly, we see the loading of a .NET assembly, basically my assembly without a path, which is a strong indicator of an in-memory assembly loading technique. Subsequently, after looking at what the assembly is doing, we see that it actually calls upon a constructor, which is basically how a typical .NET object invokes itself. And if you look at the indicators that we detected here, it's actually very similar to what we discussed earlier about in-memory assembly loading attempting to reference an assembly and creating an object out of it. And so we're actually able to have visibility over in-memory assembly loads with the use of those two events that I previously mentioned. Now, let's move on to another indicator. Let's move on to the indicator related to the use of .NET API to do registry creation. So, just-in-time ETW events, we use it to quite great success just now. So, can we use it again? Can we use this to help us in our detection? So, sadly, just-in-time compilation do not occur for native .NET assembly. And what I mean by native .NET assembly, I mean like this particular system.text assembly. As a C# programmer, if you were to reference this system.text assembly, you're able to use the function console.writeLine. So this is essentially an example of a native .NET assembly. So why though? Why doesn't this occur? Well, when the .NET framework is first installed, all the relevant .NET native assemblies will be installed as well. And once they're installed, they'll be compiled. And upon compilation, they'll be cached by something known as the native image generator, the NGen. which basically will compile .NET assemblies to native images and cache them. And because once they are cached, just-in-time compilation will not occur. And because they will not occur, there will be no just-in-time events for us to look at. So essentially, we are not at a very good place for indicators related to the use of native .NET API. So now I'm going to move on to the last indicator, indicators related to the invoking of native API. So if you remember from my previous demonstration, I actually popped a message box through the use of native API, which I imported from user32.dll. Essentially, the name of this function is message box, which I basically imported from the Windows libraries. And fortunately for us, there's a way to detect it, and it's something known as interrupt events. So interrupt events are essentially events that are generated wherever a call is made towards a Windows native API by a .NET application. So to just give a sample output from my POC script, we're actually able to detect a call towards the message box function, which is a native function from my .NET assembly. And native API by itself is very useful. Like, you're able to, like, with native API, you can pop a message box. You can actually use it to do outbound network connections. But as usual, bad guys, tractors, they can always abuse it. And these are some of the interesting activities they can do if they abuse it, like logging out keystrokes, extracting credentials from memory, or any other malicious activity that you guys can, the tractors or the bad guys can potentially think of. So in this case, having visibility over this is actually rather useful for us. So out of these 3 detection summary, 2 out of 3, so not so bad. And we're going to use what we have learned now on another demonstration. Right now, we're going to try on a real-world example, Silent Trinity. So Silent Trinity is a post-exploitation agent that is built in IronPython. Essentially, IronPython is Python that has the ability to call upon the .NET assembly libraries. With it, we're going to see whether we can detect the launch of a .NET assembly. And with Silent Trinity, I'm going to do something bad now. Instead of just popping a message box, I'm going to launch SafetyCat, a credential extraction tool. So let's move on to the demonstration. So on my left here, or rather on your right, I have a console that has my msbuild.xml Silent Trinity stager. So this contains the stager for my Silent Trinity, and I'm going to run it with msbuild.exe. And on your left, I have a Python POC script right here, which is basically what we wrote in concept, and it's the one that is going to be used to consume the .NET ECW events. So I'm just going to run the Python script in a minute, I guess. Yeah, I'm going to run it now. Then I'm going to run my Silent Trinity stager. And you can see, whoo, whole lot of output. I mean, it's event tracing, right? You expect a lot of output from here. So we're going to ignore all this output for now. And I'm going to move to my attacker's console in a minute, I think. I'm moving now. So basically, I'm going to run SafetyCats right now. I'm going to dump credentials from memory. And here, we actually got the credentials out. So cool. Now, let's move back to our detection machine. And you can see we're still getting a lot of output. And frankly, we're going to ignore all this again because I actually filter out the important information for us to look at. And that is what you want to expect to do in the real world. In the real world, you are faced with a lot of different data at one go. And it's our job as cybersecurity professionals to actually filter out the necessary information for us to look at. So right here, firstly, we actually see some interesting assembly loads. We actually see the loading of quite a bit of IronPython assemblies without a lack of path, which is a strong indicator of an in-memory assembly load technique. So IronPython by itself is not malicious, right? It's just a module for you to run IronPython. But if you see in an organization, that's definitely very anonymous. And if you see without a path, then you probably want to take note of it as well. So subsequently, let's look at other indicators that we can see in a minute again. So I'm going to scroll down now, I guess. And if you see here, we actually see a couple of interesting native API calls like virtual alloc, load library, get process address, typical API commonly found in many Windows processes, but can also be abused by threat actors for code injection purposes. And lastly, there's a native API that I want you guys to look at, which is more specific to the evidence of safety cat execution. I should be scrolling up in now. So this is known as mini dump write dump. It's a native API that allows a process to grab a handle on another process and dump its contents, which is quite similar to how you expect a credential extraction process to behave. So this level of visibility allows us to quickly decide, or rather have some form of visibility on what a threat actor is attempting to perform on Windows X8. So to just give a rough summary of the various .NET telemetries that I have spoken of. Firstly, .NET Runtime DLL. Essentially, we can do a hunt for processes that has .NET Runtime DLL within them. And for these binaries that typically do not execute .NET code, having a .NET Runtime DLL within it is rather suspicious. We can also look at .NET ECW events. With these events, we can actually attempt to trace what a threat actor is attempting to do on a Windows machine. And if you look back into the cyber kill chain, there are other telemetries that we can actually refer to. .NET telemetries are useful enough, but there are other events that we can also look at. So you expect like a .NET code execution to occur on the execution phase of a cyber kill chain, but typically you can actually use it to do your persistency. You can use it to send outbound connections to connect to your C2, but all these leave different indicators. For example, if you do persist, the indicators you leave might be different. Like for example, we can hunt for persistency indicators through the registry. We can hunt for persistency indicators through the scheduled tasks. For command control, we can actually hunt for the presence of a C2 channel by looking at network outbound connections. And how about even before the entire execution occurred? How did the attacker actually got into your network? How was it delivered? Was it delivered through a HA file? Was it delivered through a XML file? So .NET telemetries by itself is useful, but if you combine it with other telemetries built on from the entire cyber kill chain, you can actually paint a greater picture and determine what actually occurred on a single X-state. So to just give a summary of what we have discussed throughout this entire presentation, PowerShell is still deadly, definitely. I mean, threat actors still use it. I still see it commonly on my client X-states, but there are various challenges that PowerShell face right now. There are different defenses mechanisms against PowerShell. So different attackers, different bad guys have moved on to different set of techniques and attack, and .NET being one of them. But as I showed you today, .NET attacks are not that invisible as what we thought. There are still telemetries indicators that we as defenders can leverage on. And lastly, the most important point is to try it out yourself. Everything that I've shown today is open source. Like you could grab our Python POC script from our common site GitHub. .NET J script, James Forshaw, actually, you can get it from his Git. Process Hacker, you can just download it online. Silent Trinity is also easily found on GitHub. So nothing beats trying out yourself, because as cybersecurity professional, we have to constantly upskill ourselves and ensure that we are on par with the bad guys. So yeah, we have to. So for those who are interested, you can actually grab me after the talk or email me or DM me, and I can send you all the necessary links. So that'll be all for my presentation, and let's move to questions. Yeah.
Have you looked at the changes in .NET 4.8 for?
Oh yes, so I think for .NET 4.8, MZ has already been incorporated with .NET 4.8, if I'm not wrong, whereby it's actually able to track. It now acts as an interface between the .NET frameworks against the antivirus. So yeah, I'm aware of that, but I think there are still ways to bypass the MZ interface. Like I ran into several refers that they actually look into bypassing this MZ, even they are loaded in the .NET. So to answer the question, yes, I look at it, but I haven't really dig very deep into it to give a definite answer yet. Yeah.